First of all, thanks to the organizers for involving me in this nice talk series. It's a pleasure to be here. Today, I will discuss about how to tailor interfaces and Halide Perovskites to improve not only the performances of devices, but also their stability. So I will start with a short background on defects in perovskites and what surface treatments are used normally for. Present an example of interface treatments in perovskite devices, and then go investigate the thermal stability of surface treated interfaces, and also trying to understand the kind of structure that we want at the interface. So in perovskites, as in any material, we can have point defects or extended defects, 1, 2, or 3-dimensional. The advantage of perovskite materials is that, differently from many other semiconductors, where the top and bottom of the valence and conduction bands are formed by bonding and antibonding orbitals. So if we remove an atom, we'll create normally defect states, electronic states within the band gap of the material, which will contribute to non-radiative recombination. In perovskites, the top of the valence band is mostly formed by antibonding orbitals, whereas the bottom of the conduction bands have mostly a bonding character. As such, if we remove an atom, we will form either states within the valence and conduction band or very shallow defect states nearby these band edges. And this makes it so that carriers will be more easily detrapped by thermal contributions, and non-radiative recombination will be less important. However, we can also have impacts on the performances due to defects. As an example, via extended defects, where we have aggregates of one of the precursor materials, grain boundaries, and most importantly, surfaces. And even point defects at surfaces might contribute to non-radiative recombination. In a device, we are bound to have interfaces. We need election and dole transporting materials to extract the carriers. And it has been shown nicely by many different works that the presence of interfaces have an impact on recombination, which can be visualized by drops in the open circuit voltage of devices, as well as in the photoluminescence of devices. So if we were able to reduce this radiative recombination at interfaces, we'll be able to harness higher power conversion efficiencies. And this has been done in different works. The most promising approach so far is the use of bulky organic salts coupled generally with halides as counterions at the surface of 3D perovskite layers, which have enabled the highest performances to date. So how this passivation works? Well, we have our 3D lattice. We introduce at the surface a large organic cation, and this can either sit on the very top surface of the material, or even lead to reconstruction of the interface to structures of low dimensionality. In this case, I'm showing a so-called rootless and popper structure with n = 2, where n is the number of corner-sharing lead-halide octahedra spaced by the bulky cations. Passivation then can electronically can happen in different ways. We can have interaction with vacancies as an example at the top surface. We also can have prevention of recombination across an interface. As an example, if we have interface between perovskite and a charge transport layer, which is non-ideal due to presence of traps or a bad energy alignment, we could have the wrong type of carrier recombine across the interface and thus increase recombination. The use of bulky cations or of materials with a larger band gap can create tunneling junctions if properly controlled in thickness, and this could reduce this unwanted recombination pathway. Another alternative is instead having a fairly thick insulating layer at the top surface of perovskites, which however is not uniform, so has some degree of porosity or areas with lower thickness from which charges can be extracted via funneling. So we still have some passivation, but will not affect charge extraction thanks to this heterogeneity of the surface. To summarize, 3D perovskites are generally with narrower band gap than lower dimensionality. Materials have higher mobilities, but they're sensitive to moisture and oxygen, and generally to high temperatures due to the use of smaller cations, of organic cations that can vaporize under high thermal stress. In turn, lower dimensionality structures, which are kind of like derived from these 3D lattices by inserting larger bulky cations, have larger band gaps, lower mobilities, but then are more robust to oxygen and moisture and robust to higher temperatures. So just to show now an example of the use of these bulky cations, we have as an example a layer of formamidinium lead triiodide, which we surface treat with phenethylammonium iodide in isopropanol. And we make solar cells and we get very nice efficiencies, around 20%, with an improvement with respect to the pristine layer, not treated with the phenethylammonium iodide, in the voltages, which is expected if we are reducing relative recombination, but also in the currents. And this might be a bit counterintuitive because we're expecting to put an extra layer at the interface, which might reduce the efficacy of charge collection. So to understand this enhancement, we can take a step back and start by looking at photoluminescence in these layers. In cyan, we can see the PL of formamidinium lead triiodide, which in this case is very broad and it's indicative of a layer which degraded. I should mention that these measurements are taken in air. And we have large amounts of secondary phases that result in this very broad emission. Then, as soon as we introduce the phenethylammonium iodide, we see that the emission that we would expect from a material like formamidinium lead triiodide is restored. We have a narrow photoluminescence, significantly increased PL signal. However, we also do see that annealing of these interfaces post deposition of the bulky cations seems to have some sort of impact, which I will discuss more in depth later, about the efficacy of this passivation with a decrease in the photoluminescence emission. And similar trends are observed by looking at transient photoluminescence, where we look at the decay of the emission in time of these materials, which again is representative of non-relative recombination. So faster decays are implying faster non-relative recombination. In non-passivated formamidinium lead triiodide, we have the fastest dynamics. Upon introduction of phenethylammonium, we slow down this recombination, but again, annealing fastens it up. And these dynamics could explain the enhancement in open circuit voltages that we saw in passivated films. To explain the difference in currents, we can look at measurements of terahertz photoconductivity, from which we can extract the local mobility of these carriers. And what we see is that as soon as we introduce phenethylammonium on the top surface, the mobilities are improved. Annealing decreases a bit these mobilities, but they still remain higher than in the pristine film. So there are some changes in the structure of this material, which affect also the bulk, which are enhancing its property and which might explain the improvement in currents. An hypothesis might be the interaction with air, as I mentioned, since we're doing all of this characterization in presence of oxygen and moisture. So to try to understand better what is going on at these interfaces, we can use grazing incidence wide angle X-ray scattering. I will not go in depth into the description of this technique, as Rhiannon Kennard provided a very nice introduction to this tool set in a previous talk at NGSE. I will just mention that it's related to XRD. XRD probes diffraction only along this direction. So it's planes that have an orientation parallel to our substrates. GWOX is able also to probe diffraction from crystalline planes that are oriented perpendicular to the substrate or at angles. And the Q that we measure in GWOX is related to the spacing between lattice planes reciprocally, and can also be related to the Chu theta, which we measure in common XRD plots. An advantage of GWOX for measuring studying surfaces is that we have very good control of the angle with which we impinge on our substrate, and as such we can go below the critical angle, so the angle at which we have total reflection of the X-rays from the surface of our material. And these allow us to probe via an evanescent wave only the top few nanometers of the film. If we increase the angle above this critical value, we can probe deeper into the film and get information about the bulk behavior and crystal phases, with a value of about 0.1 degree, which is commonly observed for Halide perovskites. Just to understand a bit more what GWOX means, well, if we have a very disordered material, we'll have a specific plane which have any possible orientation with respect to our substrate, and we'll get this kind of diffraction ring. If we progressively increase the order, we'll start to have all crystallites oriented in the same direction up to the extreme case of a single crystal. And this will mean that a specific plane will create a specific diffraction spot in the GWOX diffractogram. So now we can try to understand the behavior of formamidinium pristine films in the bulkhead at the surface. We can look at integrated patterns. So we just take a circular integration of the GWOX and plot it in a similar fashion to XRD as an example. And what we see is that in these patterns, we have 001 diffraction, which is characteristic of the cubic phase of formamidinium lead triiodide. But we also have a secondary peak at smaller Q values, which is associated with hexagonal phases forming, especially at the surface of this layer. And these hexagonal phases are degradation byproducts of the cubic phase, which are photoinactive and insulating, and can introduce recombination. So what is going on is that we are creating hexagonal phases at the interface of the formamidinium layer, and these are causing recombination and decreasing the performances of our film. We introduce phenethyl ammonium iodide at the surface, and we immediately see that these secondary phases are suppressed, and we do see the formation of a 2D layer at the very top surface of our films. So the phenethyl ammonium iodide treatment is preventing somehow the formation of this or the degradation of our 3D formamidinium lead triiodide layer here. How can we explain it? We can use another surface sensitive technique, which is X-ray photoelectron spectroscopy. We still use X-rays to excite the surface of our samples. X-rays remove electrons from the core shells of atoms at the surface, and by measuring the kinetic energy of these electrons, we're able to determine which elements are present at the surface and what are their chemical bonds. And if we look at oxygen, we see that in pristine films, we do have a peak for oxygen, but as soon as we use the bulky cations, this peak disappears. So these cations are preventing interactions of oxygen and moisture at the surface with these 3D perovskites. And as a matter of fact, if we look at in situ measurements in nitrogen on the 3D perovskite, we see that this phase is pretty stable in an earth environment. So the main role of this surface treatment, as an example for pristine formamidinium lead triiodide, is actually of a barrier layer. And it prevents the interaction with oxygen and moisture, which in turn lead to this transformation to hexagonal phases of the surface, which then cause degradation of the pristine layer performances. However, as I mentioned before, we also see variations with annealing. What is the impact of annealing? Well, what we see is that if we stress these surfaces before exposing them to moisture, we start again seeing the appearance of these hexagonal phases. So again, we do start to see recombination happening at the interface, and this lowers performances. And this is also been observed in other reports and literature, which claim that actually after annealing, the passivation either disappeared, but also in an opposite fashion, other reports showing actually that annealing could be beneficial. So to try to go deeper into what is happening at the interface, we try to devote our attention just to the thermal study. And we took up 3D layer, treated it with a bulky cation, again, phenethyl ammonium iodide in this case, and then thermally stressed this stack for different time duration at an extreme temperature of 100 degrees Celsius. Again, we studied this with grazing incidence, wide-angle X-ray scattering. And here we see the pristine film before the treatment. We see that the crystal lights are randomly oriented at the surface with a very nice clear diffraction from a cubic lattice. We introduce phenethylammonium, and immediately we see the appearance of diffraction associated to 2D structures at low Q values. And these structures are associated to this Rudless and Popper phase with unequal Q. So two planes of corner sharing lead halide octahedra spaced by this bulky cation of phenethylammonium iodide. As it can be seen, diffraction is mostly along the vertical direction, which is commonly observed in lower dimensional materials, which means that these diffraction planes, which are responsible for these spots, are oriented parallel to our substrate. Once we start testing thermally these films, however, we observe that this diffraction starts to decrease in intensity and new diffraction spots start to appear at larger Q values. So what is happening is that not only we're destroying the crystallinity of our starting n equal 2 lower dimensionality layer, but also we are creating disorder in the film and formation of other low dimensionality materials. This is associated with changes in the chemistry at the surface. So if we look at the nitrogen signal and look at the NC single bond, which is representative of the phenethylammonium iodide cation, we see that this signature decreases with annealing, whereas for meridinium iodide increases in intensity. And analogously, the lead signal, which is again a marker for the presence of a perovskite structure, increases with annealing. So this points at the fact that these bulky cations are diffusing away from the surface, along with this reconstruction of the interface, which might either mean thicker layers being formed at the surface or eventually more heterogeneity also spatially being formed at the surface. What does it mean in terms of surface passivation? Well, this happens when you leave samples in air at high relative humidity. We have the pristine sample, which degrades almost completely, which is shown by the changing color of this layer, which gets yellow from the initial black. Pristine samples, as passivated, remain mostly black. But if we anneal the samples before exposing them to moisture or air, we see again degradation. Analogously, we see decreases in performances, even in pristine devices as fabricated and just exposed to thermal stress, which are also observed not only at 100 degrees, but even during maximum power point tracking under one sun illumination at temperatures which are relevant for solar operations of 55 degrees Celsius, where after about 100 hours, the phenethylammonium iodide experiences a sharp drop in performances. And it can be shown that this drop is especially related with changes in the currents in the device, with this increasing thickness of the bulky cation layer being responsible for worsened charge carrier extraction. Importantly, these variations are observed only at high temperatures. If we decrease the temperature to 25 degrees Celsius, all these dynamics are masked. So it is very important when you test 2D, 3D structures to test those at different temperature ranges to try to reveal these hidden degradation dynamics. This leads me to the last part of this talk, which is about the structure at the interface and what we can do about this degradation. And is there a solution to also try to enhance stability? One part of the story is that we can have very different interfaces after the treatment with these bulky cations. We can have the cations only sitting at the top surface, reconstructing the surface, either forming a pure phase or mixes of phases, eventually also with heterogeneity in the coverage, which is the most common case. But how does this also correlate with the thermal stability that we see in the layers? And these variations also correlate with what we're expecting these materials and these interfaces to do. If we're expecting only passivation of point defects, well, a bulky cation layer might be what we want without reconstruction. If we want a tunneling junction, we want really good control of this interface, but we don't want to make it too thick to prevent charge carrier extraction. And if we have thicker layers, we might want heterogeneity spatially to prevent issues with the charge carrier extraction. To try to study this, we explore different deposition routes. The most commonly used for bulky cations is the deposition of phenethylammonium iodide from isopropanol, but this results in a lot of limitations. Isopropanol is a very volatile, so it results in very poor control on the thickness that we deposit, possibly spatial heterogeneities, and also solvent damage of the surface of the perovskite layer. Vapor deposition bypasses these limitations in principle. So we then deposit these layers on top of a 3D perovskite, and we characterize again the diffraction from the surface. And we see clear differences. In the case of solution, we can see that we have two main diffraction peaks at low angles, which are associated with an N=1 and N=2 relevance popper perovskites, which are schematized at the surface here. Whereas via vapor, we get dominantly N=2 perovskite layer. Relevance popper phase. Besides, we see differences also in the surface morphology. Deposition via solution results in the formation of aggregates at the surface of the perovskite film, which are formed by phenethylammonium iodide aggregates, whereas in the vapor-treated films, we do not see aggregates, and we see a fairly uniform surface. Annealing results in a reorganization of the structure. The signatures of phenethylammonium iodide aggregates disappear, and we see the formation of an overlayer, which masks partially the underlying structure and morphology of the perovskite film. Whereas in the vapor film, we seem to have an improvement in crystallinity, but we still do observe clearly the underlying structure of the 3D bulk. We then can study again the purity of this interface by looking at photoluminescence. Again, when we look at PL, we see that the vapor deposited films, especially after annealing, show a very clean, pure N=2 emission, which is expected around 550 nanometers, whereas the solution deposited show mixed emission from N=1 and N=2. If we do photoluminescence maps of the surface, which can give us an idea of heterogeneity at this interface, what we see is that we have very low emission before thermal annealing from the solution deposited film. After annealing, we get very uniform emission, which suggests a very continuous coverage of the structure and likely a fairly thick N=2 relevance popper layer being formed. Via vapor, instead, we do observe some heterogeneity, which becomes more clear and visible after a short annealing of 10 minutes at 100 degrees Celsius, suggesting possibly heterogeneities in the thickness of this layer, but still a full coverage of the 3D perovskite bulk. And possibly pointing at a extraction in this case, which might be driven by thinner parts in the layer, which still allow charge extraction. If we look at performances, we can look at the open circuit voltages, and we see that in all cases, the VOC of device is enhanced with respect to the reference, particularly after annealing. However, in solution, we do see a slight decrease in the initial voltage without any thermal annealing, which is possibly related to the fact that we are creating defects at the surface of the perovskite film with isopropanol treatment. The biggest difference, however, is the behavior under thermal stress of these devices with short annealing. In the vapor case, where we see these variations in photoluminescence with annealing, we see an enhancement in the charge carrier extraction of these layers, which leads to improved performances. In the solution case, instead, we see a drop in charge carrier extraction, which leads to worsened performances with respect to the pristine and annealed films. And another advantage of vapor deposition is the fact that the phase purity of these interfaces seems to result in very narrow performance distribution, which is very beneficial if we're thinking about large area devices and also about reproducibility. So this leads me to my conclusions and to some take-home messages. I hope I've shown that bulky cations have a very important role in preventing the interface degradation in perovskites upon exposure to moisture and oxygen. And this is a big driver of reduced recombination at the interface that shouldn't be neglected. The interfaces of 2D, 3D perovskites, even though pure 2D might be stable, these interfaces are not and are subject to a continuous evolution in structure under thermal stress. which can result in performance loss. And we can reduce the impacts of these drop in performances under thermal stress by making either thinner interfaces or benefiting from local variations in thickness of these 2D, 3D layers. However, I guess the long-term and goal would be to probably go towards molecules that do not really reconstruct these interfaces, but are able to protect the 3D perovskite and interact with point defects at the surface without reconstructing the bulk. And these will probably lead to high energy yields, so high efficiency and high stability perovskite solar cells in the future. I would like to conclude thanking, first of all, my group for the great work and support. Juanita Hidalgo contributed to a lot of the work with GWOX that I presented today, and our collaborators at the various universities, as well as the funding sources, and all of you for the attention. And I open now the floor for questions.